we are going to the final presentation given by Vedika Khemani. She is assistant professor of physics and also applied physics at Stanford University. I just would like to mention that in 2016, she was having a very important paper called Phase Structure of Driven Quantum System, published in Physical Review Letters. And in this paper, she was triggering a lot of activity about how to build time crystals. And I think this is the topic also of her talk today. It's entitled Many-Body Physics in the NISQ Era, Quantum Programming a Discrete Time Crystal. Please, Vedika, go ahead. Unmute yourself, please. Or Anka, can you unmute Vedika, and then you have to share.
Okay, I think I'm unmuted.
I already see it, yes, that's fine.
Yeah, and my screen should be sharing, right?
Yeah.
Okay, great. Yeah, thanks very much to the organizers for this kind invitation and for putting together this really nice virtual conference to make the most of the circumstances. Today I'll be telling you about some work that actually dovetails quite nicely with the last talk, because I'll be specifically discussing what kinds of many-body physics we can do with these NISQ devices. Okay, so this talk was led by my postdoc Matteo Ippoliti, who's at Stanford, also in collaboration with Kostya Kajetsi at Google, Roderick Morsner at Max Planck Dresden, and Shivaji Sondhi at Princeton. Okay. So, right. So we just heard from John this wonderful account of this milestone development by the Google team, and their announcements signal in a very clear way that after a decades-long effort to design platforms for individual quantum circuit elements and to demonstrate their functionality in small-scale proof-of-principle experiments, we're finally at the stage where all of these technologies can be deployed to address real-world scientific problems, okay? And while the ultimate goal of a fault-tolerant universal quantum computer is still far into the future, the possibility of harnessing the computational power of the quantum world with these noisy intermediate-scale quantum devices or NISQ devices is already a reality, right? And as exemplified by this conference, this really represents a multi-pronged global research effort across academia and industry, and as part of this continuing evolution in the development of artificial or designer many-body quantum systems across a variety of platforms ranging from superconducting qubits to trapped ions. Right. So, you know, in John's talk, he already referred to immediate applications for these NISQ devices, say in quantum chemistry simulations or for optimization algorithms. But, you know, a quantum computer is also necessarily a highly controllable many-body system with a sizable Hilbert space. And so these advances are also extremely tantalizing to many-body physicists. And, you know, these devices bring new capabilities, so it's natural to ask, what new kinds of physics can they host and discover when viewed as experimental platforms for many-body physics, okay? And you know, this dual view of these computational devices as information theoretic tools on one hand and as experimental platforms for many-body physics on the other is, I think, one of the most intellectually interesting hallmarks of this NISQ era, okay? So this work and my talk broadly is motivated by the question of what does this NISQ era of tunable, programmable quantum systems portend for many-body physics, okay? In particular, which physical phenomena in the realm of quantum statistical mechanics can these devices realize that have either not been or cannot be as crisply demonstrated in any other setting? And narrowly, I'll focus on what interesting physics can be realized immediately with Google's Sycamore device, okay? Now, this program immediately presents a couple of conceptual leaps or conceptual challenges, because, you know, in condensed matter physics, we typically tend to look for new kinds of emergent phenomena in many-body systems in thermal equilibrium, usually near zero temperature or at low temperatures, right? And while we can get all sorts of interesting quantum orders, quantum correlations in this low temperature regime, The high temperature physics is usually thought of as non-universal or thermal or classical, right? On the other hand, the natural time evolutions that are implemented in these gate-based quantum devices, such as Sycamore, are quantum circuits rather than Hamiltonians, okay? And the trade-offs between unitary control and platform size inevitably builds in some amount of variation in these individual circuit elements, so that this presents some kind of challenge for simulating very fine-tuned model systems where you may need to know all the parameters very, very precisely, okay? So I want to emphasize here that, I want to be thinking of these devices not as universal quantum computers, but as experimental platforms for many-body physics, okay? Of course, it's true that as a computational device, once these platforms are of sufficient size and have fault tolerance, they can simulate absolutely anything, okay? And you can solve the ground state of the Hubbard model with it. But right now, we're interested in the physics that these platforms can immediately and naturally realize versus physics that they can universally and asymptotically realize, okay? So that's the program, and it really requires this kind of conceptual shift in many-body physics from thinking about Hamiltonians to thinking about unitary circuits, okay? And indeed, this setting of starting with different initial states and doing time evolution is precisely the domain of non-equilibrium quantum mechanics, okay, or non-equilibrium quantum dynamics. So a parallel set of developments in quantum statistical mechanics actually furnishes a very natural domain where the specific challenges, the specific conceptual leaps turn into strengths, okay? And this is the study of non-equilibrium quantum dynamics, and specifically the assignation of robust phase structure to many-body systems out of equilibrium. Okay, so I won't have time to go into any of this in any amount of detail, but I just want to give you like a high-level view of what we're talking about, okay? So here we have in mind systems that never reach thermal equilibrium. So, usually when we're talking about quantum systems, you have in mind a system and it's either coupled to some reservoir or bath. It reaches thermal equilibrium as a result of this exchanging energy or particles with the bath. And then you can talk about phases or phase structure in equilibrium states of these many-body systems, okay? But, at the first step, we're stepping away from systems coupled to baths to isolated or closed many-body systems, okay? And these systems can still reach local thermal equilibrium in a sense where local subregions of the system can view the rest of the system as a bath and still reach equilibrium. And then you can describe phases and phase transitions again in these in these closed quantum systems in quite the same way, okay? But now I have in mind a setting, which is a setting of many-body localization, where this kind of local thermal equilibrium is never reached, okay? So the system for all times, for infinitely late times, is going to retain some local memory about its initial condition, okay? And then further, I have in mind systems that are going to be periodically driven, okay? So in this very, very non-equilibrium, this intrinsically non-equilibrium setting of periodically driven systems that are many-body localized, never reach local thermal equilibrium, one realization that was quite interesting was the fact that even though equilibrium thermodynamics goes out the window, so all the usual ways that we have of thinking about phases and phases of matter and the transitions between them, even though all of that structure goes out the window, phase structure need not go out of the window, okay? So now, just as you have various kinds of phases for systems in thermal equilibrium, you can similarly have many different kinds of phases that are sharply distinct from each other for localized systems out of equilibrium, okay? So in particular, you could have a localized spin glasses or localized paramagnets, or what I'll be talking about today, which is localized time crystals, okay? And the reason that what's even more remarkable is that not only can you get different kinds of phases out of equilibrium, but actually the localization can allow for new kinds of quantum order, specifically new kinds of non-equilibrium quantum order that may be forbidden by the strictures of equilibrium thermodynamics, okay? So this leads us to our specific proposal, which is we plan to use this Sycamore device to realize a time crystal, which is a specific non-equilibrium phase of matter with a particular pattern of spatiotemporal order, okay? Now, some of you have no doubt seen some headline results on experiments in time crystals from a few years ago. So you may be wondering, why is the Sycamore device so special? What unique capabilities does it bring for this program of realizing this time crystal? right? But, you know, as time has gone by and we've looked at the experiments that were done more and more carefully, what we realized is that a genuine realization of this phase, or for that matter, actually any of these novel non-equilibrium phases of matter, has proved elusive for different reasons in each of the existing platforms in which it has been explored, okay? And indeed, there are fundamental definitional aspects of the physics of this time crystal phase that have not yet been observed, and indeed cannot be observed with the existing state-of-the-art experiments. Okay. So for the rest of this talk, I'm going to first just briefly review the features of this time crystal phase. I'm going to give you a summary of the state-of-the-art in experiments, and this will allow me to do is to pinpoint what are the desired experimental capabilities that we need to see a genuine incarnation of this phase. And then we'll see how the Sycamore platform actually checks all of these boxes very, very nicely. It can realize a model. This model has a phase diagram, which has an extended time crystal phase, and then I'll present some diagnostics of this phase and the effect of environmental noise that's going to be present, okay? So to step back, you know, what is a time crystal? Okay, in one line, a time crystal is a phase that spontaneously breaks time translation symmetry. In physics, we always think about phases and phases of matter as being defined by some kind of symmetry breaking, but perhaps the most fundamental symmetry of all is that of time translation symmetry in a time-independent Hamiltonian. So in a time crystal, while the rules underlying the system are time independent, the motion or the state of the system is periodic in time. Okay, so this represents the spontaneous emergence of a clock, if you will. So, you know, there's been a lot of activity in this area, and, you know, immediately going back decades, but perhaps more broadly going back centuries. Okay, because this idea of a time crystal is perilously close to a perpetual motion machine. And, you know, I can't go into all the subtleties, but actually defining this phase in a crisp sense, I direct you to this review that we wrote last year on this. But the punchline is that if you think through how carefully to define this phase, what we find is that this is a phase that is forbidden in thermal equilibrium states or in ground states of many body systems, okay? So there is a very specific setting in which we're going to be able to get around this kind of no-go theorem and realize this phase in a many-body sense, okay? And again, without going into details, I'm just going to tell you the 4 features that we'll need to realize this phase, okay? So equilibrium or ground states of time-independent Hamiltonians are out the window. Instead, what we're going to consider is periodically driven systems. These are the so-called Floquet systems. In these systems, you don't have continuous time translation symmetry, so your equations of motions are not invariant under time, okay? But what we have is a discrete time translation symmetry. So the system, the equations of motions are invariant under translations by multiples of this driving period, okay? On the other hand, while the system has this discrete translation symmetry by multiples by translations with t, observables show period doubling, okay, or observables show response at multiples of the driving period. Okay, so this spontaneously breaks the discrete time translation symmetry, and it gives you this kind of sharp subharmonic peak in Fourier space. Okay, so this is the kind of simplest dynamical diagnostic, this issue of period doubling in a periodically driven system. Okay. What's more, what we need to define a phase of matter is that this period doubling should persist in a robust way over a range of parameters so as to define a phase of matter, okay? We're going to need many body localization to avoid heating to infinite temperature. Anytime you have a genuinely interacting many body system that is periodically driven, you know that under equilibrium thermodynamics, the system is just going to try to maximize its entropy, and the maximum entropy state in the absence of any conservation laws is just the infinite temperature state. Okay, so we need MBL to avoid this heat death. And finally, a signature of this phase is spatiotemporal order. So, you know, so we don't want to be considering only this period doubling in time, but actually in this phase, this system displays this very novel kind of correlated spatiotemporal order where it has long range order in space and period doubling in time. Okay, and this is going to be a signature of this phase. Okay. Good. So, some of you, as soon as people hear period doubling, it invokes a lot of knee-jerk reactions to nominally similar phenomena that have been observed across a range of familiar systems, going back many, many centuries. Again, in the study of dynamical systems, it ranges from parametric oscillators to Faraday waves, as we, again, I won't have time to go into this, but as we discussed in great depth in this review, all of these more familiar examples, so period doubling is not the only thing we're looking for, okay? We're looking for this correlated spatiotemporal order in a genuinely many-body system, okay? And all of these familiar examples, when you analyze them more carefully, they're all one or few or, effectively few-body systems in some mean field sense, okay? Whereas we're interested in this genuine many-body phase of matter for systems in some infinite size limit, looking for infinite times, okay? Because that's the setting in which, as condensed matter physicists, we're going to sharply define phases of matter, okay? So this setting requires Floquet many-body localization and the criteria that I listed on the previous slide, okay? So good, and these criteria are actually not satisfied by any of the experiments in a completely genuine way, okay? And that's why it leaves open this exciting window to observe it on this NISQ platform, okay? So to situate ourselves, I'm going to start with a very simple model for a very simple model that realizes this phase, okay? And then we'll see how a variant of that model can be easily realized in the Sycamore platform, okay? So, okay, yeah, actually, and before going there, I should say that, I repeat, like, why we're considering this time crystal for Sycamore is that it is a novel non-equilibrium many-body phase of matter with spatiotemporal order that has not been achieved in experiment yet. When we consider models for this phase, we'll see that circuit realizations of these models, again, Sycamore is going to do this kind of unitary circuit evolution rather than evolution with type-independent Hamiltonians. And the circuit realizations are actually very natural when thinking about time crystals. The signatures of this phase, the crispest signatures of this phase, are in the dynamics of the problem, which Sycamore is, again, well suited to probe. You prepare some initial states, you time evolve it, and then the diagnostics of this phase are in those dynamics. It's the dynamical non-equilibrium phase of matter. So it's not in equilibrium thermodynamics. And finally, if the experimental platform has variations in its circuit elements, just because of finite calibration capabilities, that disorder is not only tolerated for this platform, but it's actually essential for stabilizing MBL. So, one of the things we'll talk about is that it's great for us if the system can be made very, very disordered. And that's something that's very easy to do in these circuit settings. Okay. So now let me turn to this simple model for a time crystal, okay? And this is a model of a periodically driven Ising chain, okay? So you have in mind some Hamiltonian. It's switching. We have a chain of spin 1/2 in one dimension. This Hamiltonian switches between two evolutions. Okay, in the first part of the in the first part of the period, you're evolving with hx, which is just a uniform field in the x direction. Okay, and this part of the drive enacts rotations of z product states about the x-axis. Okay, and in the second part of the drive, we're evolving with this hz Hamiltonian. Okay, so this hz is just going to look like a nearest neighbor Ising coupling. Okay, and then for your actual time evolution, you're just going to repeat this one period. So this u Floquet is the time evolution operator over one period. Okay, so you first act with this Ising interaction term, then you act with this rotation about the x-axis, and you can repeat that many, many times. Okay, so this model is actually just a free fermion model. Okay, it's nearest neighbor Ising interactions and a transverse field in one dimension. It's just a periodically driven 1D transverse field Ising model. This is exactly solvable, and you can map out its entire phase diagram. And what you find is that as a function of these two parameters, which is average J and average G, you get 4 different phases. 2 of these, don't worry about what these labels are. 2 of these phases are exist in a non-driven setting, but 2 are unique to this periodically driven setting. Okay, and one of these is this time crystal phase. Okay, So it's actually really easy to get an intuition for what's going on at an exactly solvable set of points in this parameter space. Okay, so consider the limit where this transverse field is set exactly to pi over 2. Okay, so when that's set exactly to pi over 2, what we know is that you're enacting this perfect pi flip, or this perfect 180-degree rotation about the x-axis. Okay, so at this along this line, right? That's what this line is when g is pi over 2. You time evolve your Hamiltonian with this Ising-Z coupling, and then you enact this perfect pi flip. Okay, so this is this pi rotation and the Z coupling. So it's extremely easy to see what's going on here, right? If you start with some product state in the Z basis, you time evolve it under HZ, it picks up some phase, then you enact this perfect pi rotation, so all the spins flip, and then you do this again and again and again. Okay, so this kind of, very, very trivially shows you period doubling, because if you go in and you measure sigma z on some one site, you'll see it's this period double response, because it switches sign and only comes back to itself every 2 periods. Okay, and what you also see in these problems, so this is the SG here refers to spin glass. Okay, so this phase also has glassy long range order in space. Okay, so that's the spatiotemporal business. So temporal refers to this period doubling in time, and spatial refers to a glassy long range spatial order. This can be diagnosed most crisply by looking at the eigenstates and eigenvalues of this Floquet unitary. We don't have to get into that. There are also crisp dynamical signatures, but the main punchline is that in this space, not only do you have period doubling, but you've also spontaneously broken this Ising symmetry to display long range order in space. Okay, and usually if you break Ising symmetry and you have some kind of ordered ferromagnet, that's diagnosed by measuring some spin-spin correlation function at large distances and looking for something non-zero. So here we're doing something similar. You are still measuring some spin-spin correlation function, but instead of getting something that's in a ferromagnet, all your spins will be aligned and the spin-spin correlation function will give you something non-zero and positive. Here you get something glassy. Okay, so depending on, you have all of these patterns of domain walls. This is a localized system, so your configurations look like these frozen patterns of spins. So when you go in and measure this correlation function, you'll get something non-zero, but with fluctuating or random sign. Okay, so that's what this glassy refers to. So if you measure the correlation between these two spins, for instance, depending on whether you cross an even or odd number of domain walls, you'll get something +1 or -1. Okay, so exactly along this this exactly solvable line, you can see in a very transparent way why you have both period doubling and glassy long range order. But if this was the whole story, this would be utterly non-remarkable. I'm literally coming in and exactly flipping the spins. So of course I get period doubling. There's no big deal about this. Okay, so the really interesting feature about this is that this behavior along this one line actually persists into a very robust phase of matter with genuine spatiotemporal order, even once you perturb away from the exactly solvable point in various ways. Okay, so some of the ways in which you perturb away from it is, instead of having this rotation angle be exactly pi, as you tune your G, you actually enact imperfect rotations. Okay, so for instance, instead of flipping your spins completely by 180 degrees, you can flip them by 180 minus some error, okay, minus some epsilon, which is controlled by this angle. And you can add in all sorts of interactions to your to the Ising coupling part, and these interactions will generally make your system interacting. Okay, so it's no longer going to be this free fermion system. So we could add in longitudinal fields, and the interactions that you add in could explicitly break the Ising symmetry that you had to start with. You could add in some XX plus YY type couplings. You can add in all sorts of weak interactions. Okay, and I also, I can really perturb this in any possible way. Okay, so I don't have to separate it into perturbations of this HZ that sit in the first part of the period and only these rotations. I could have done all sorts of things even in the second half. Okay, so the main point is that this is an exceptionally robust phase of matter. Okay, usually we know when we're thinking about symmetry and symmetry breaking, you have in mind like you have an Ising symmetry, but if you explicitly break the Ising symmetry, it no longer makes sense to talk about a ferromagnet. But in this case, you can really perturb the system with whatever you want, and you still get this robust, stable phase of matter that shows long range order in space and period doubling in time. Okay, so this kind of this was immediately met with proposals for many different experiments on many different platforms. And the reason is that, this kind of robustness of the space, so, you can perturb it with anything. It doesn't matter if your experiment hasn't like finely tuned, hasn't realized one thing or another in some fine-tuned way. So this robustness of the phase coupled with the sharp dynamical signatures immediately led to a series of experiments on this. Okay, so this is, there were two early experiments in disordered systems. The first was on a platform of disordered nitrogen vacancy centers in three-dimensional diamond. This was a macroscopic system. They had 10 to the 6 ions, okay, and there's really no scope for fine-tuned spatially resolved control here. And the other was an experiment on trapped ions in one dimension. Here the system was much more controlled and there were only 10 ions, okay. And finally, more recently, there was a system on an ordered spatial crystal, so there's no disorder whatsoever in a 3D crystal, okay. All of these experiments had basically the same protocol. They evolved with some part of the drive which had dominantly Ising interactions. Then they enacted an imperfect rotation, and then they measured some observable like a magnetization or some global polarization. And what they found was some signal which in time showed this kind of period doubling behavior when probed every period, okay? And because this is a real experimental signal, there was inevitably some decay of this envelope due to decoherence, and they roughly went to 100 periods or so. That was the lifetime of the experiment, and then this time signal corresponds to some Fourier peak which is subharmonic at pi, okay, at pi over t, at half the frequency. Okay, so as I was saying, more careful analysis actually reveals that none of these experiments actually realize the phase, okay? So this diamond experiment, it was already known that the fact that the system is in 3 dimension with dipolar interactions which fall off as 1 over r cubed, the system was too long range to realize many body localization, and this was something that was known. So this realizes what's known as a critical time crystal where it thermalizes extremely slowly, okay? Then you can have pre-thermal time crystals. I won't have time to go into them, but these pre-thermal time crystals, they don't last infinitely long, but they only last for some finite period of time, and it could be hard in practice in an experiment with finite coherence to tell these apart if all you're looking for is the time of the signal, because the experiment is run to a finite time, okay? So analysis of these experiments helped us identify what are the necessary ingredients for actually demonstrating this phase, okay? So the first is none of the experiments measured spatiotemporal order, okay, which is the site-resolved long-range order in space, period doubling in time. To measure spatiotemporal order, you need to make measurements of site-resolved observables and to vary initial states, okay? And this varying of initial states is important because it's important to distinguish these asymptotic time crystals from their pre-thermal variants, even in an experiment that can only be run to finite time, okay? And finally, for stabilizing many-body localization, we need short-range interactions, and we need disorder in the Ising even couplings, which are these JIJs, okay? So the trapped ion setup actually meets many of these requirements, okay? You have short-range interaction, it has interactions that are short-ranged enough in a way. You can measure site-resolved observables in it, you can vary the initial states in it, but this experiment does not realize disorder in this Ising even couplings, and this is crucial for why this experiment cannot show you time crystal behavior, okay? On the other hand, as we turn to Sycamore, what we'll see is that the natural interactions in the platform are nearest neighbor gates, so it's already short-ranged, okay? You already have access to a wide range of initial states, and you already have access, you can just take a snapshot of the whole state, so you already have access to site-resolved observables, okay? So all of these features are present, and now all we have to address is the nature of the interactions, whether we can get dominantly Ising interactions with disorder in the Ising couplings, okay? But this is also extremely easy to do. So we just took the native transmon gate that exists in this experiment. It has some XX and YY couplings with some theta, and then it has a ZZ coupling with this parameter phi. And you can do some kind of, and it has some other Z rotations, but you can do various Z rotations on this native transmon gate to get this G tilde gate. And this G tilde gate just looks like rotations about the Z axis with on-site Z fields, and then this XX and YY term and this Ising term, okay? And then these parameters, theta and phi, can be chosen randomly from gate to gate. So you can easily enact this disorder in the Ising coupling. And by making theta small, you can make this Ising coupling the dominant part of the interaction. Okay, so this really gets the physics, and we did careful numerical simulations on this model that can be realized in this circuit. Okay, and actually this is the same kind of snaking that John was mentioning. Okay, so you can get this physics in 2 dimensions and so on, but it's cleanest in 1D. And in 1D, you can just do this. You can take the Sycamore device and make this 1D snake. Okay. And then you can look at this phase diagram. This phase diagram has a localized time crystal. It has a localized paramagnet and has this broad thermal region. And then by tuning the experimental parameters, you can not only observe the time crystal, but also see a transition from the time crystal into a thermal phase in a very crisp way. Okay. So what are some of the signatures? The simplest signature to understand is some kind of autocorrelator in time. So you're measuring some correlation between z of t and z of 0. You can measure this in a site resolved way, average over sites. In the time crystal, you see period doubling, okay, of this kind. In a thermal phase, this autocorrelator very, very rapidly goes to 0, whereas in a paramagnet, because it preserves local memory of its initial conditions, this autocorrelator saturates to something non-zero, but it doesn't show period doubling. Okay, so this autocorrelator immediately already tells these phases apart, but because of this platform, we can really get the full spatiotemporal information. So you can start with some pattern of spins. Okay, so this is just some random pattern of spins in space, and now you can run it in time. And what you see is that you can just visually see here that these phases look very different. In the paramagnet, this pattern is preserved in time. In the thermal phase, this pattern immediately melts. Okay, so all these expectation values go to 0, whereas in the time crystal phase, this pattern starts repeating in this alternate way. Okay, so this is like a full imaging of the state, and you can use this to define all sorts of autoparameters that are more familiar in condensed matter, like some Edwards-Anderson autoparameter, and you can use this to actually do finite size scaling and get this phase transition. Okay, so this is another feature that's unique to this platform, that just by taking snakes of different sizes, we can do finite size scaling and really get at this transition. Okay, so another diagnostic that's unique to this experiment and not any other is the ability to measure Hamming distances. Okay, so once you're time evolving your system, you can look at the distributions of what these states are doing, and you can measure how far those states are from the state in which you started. Okay, so in a thermal system, you see that immediately you started with some state, and at very short times, the state that you obtain is different from the state that you started almost everywhere. Okay, and statistically, half the sites are different. Whereas in the time crystal phase, you see that it's very similar to the state in which you started at even times, and it's exactly flipped at odd times. Whereas in the paramagnet, it just stays where it is. Okay. I want to very quickly, I'm almost done, talk about noise in these platforms. Okay. So in an actual model, we're going to have noise. John spent a while talking about this. Okay, we can do more careful noise analysis. Here we've just assumed a very simple depolarizing error model for this noise. Okay, and what this gives us, just as it does in any other platform, is a signal that decays exponentially in this way at a rate set by the noise. So this gives you these broadened Fourier peaks, and the width of the peak is set directly by the noise. Okay, but a conservative estimate of 1% in the noise still allows you to observe the signal over hundreds of periods. But one thing that I want to emphasize here is that the exquisite noise calibration in Sycamore helps us disentangle the contribution to this decay that's coming from the external decoherence versus contributions coming from sort of more internal sources of decoherence just because of thermalization. Okay, and as you keep improving noise capabilities, the signal should last longer and longer. Okay, so this is the last slide, and it's telling you that in this system, in contrast with chaotic systems, the signal decay does not care about the system size; it only cares about time. And as a result of that, because this is not a chaotic system, you're only measuring some local observables, and those only care about noise in a local patch. As a result of that, you can actually go to much larger sizes without necessarily sacrificing the lifetime of your experiment. Okay, so that's the summary. We've presented an immediate near-term application of a NISQ device as a genuine platform for many-body experiments. There's a broader set of interesting many-body problems with random circuits, ranging from entanglement dynamics to chaos to measurement-induced phase transitions. And more broadly, this view of NISQ devices as experimental platforms in their own right calls on us to devote to these setups the same level of attention commensurate to that normally devoted to other more traditional systems in condensed matter or materials physics or cold atoms. Thanks.
Yeah, thank you very much. Beautiful results. I'm very happy to see that we can use quantum machines like Sycamore to do beautiful physics and to discover new things. Stefan, did you collect questions?
Yes, I already got a number of questions. They start simple, but then we'll get more deep as we go. So what is the difference between pendulum and time crystal regarding the broken time invariance?
Great. So that's an excellent question. And this connects to a point that I was trying to emphasize when it comes to many body systems. Okay, so in defining a time crystal, it is absolutely essential to think about a many body system. Okay, because as you said, a simple harmonic oscillator or a pendulum routinely displays oscillation. So time translation symmetry breaking is absolutely trivial in this setting. Okay. And indeed, in our review, we go to the example for pendulum in a lot of detail. So for the pendulum, if you think of the pendulum as a single degree of freedom located at the center of mass of the pendulum, and you put it in a frictionless bell jar or something, then indeed this can oscillate forever. But if you think of the pendulum as a genuinely many-body system with lots of different modes all interacting with each other, then the energy that's in the center of mass mode eventually dissipates into all the other modes, as it must do because of the second law of thermodynamics, and then this pendulum eventually comes to rest. Okay, so first and second law of thermodynamics, first law tells you need some source of energy. You can get around that by sticking this in some frictionless bell jar. Second law tells you equipartition of energy means that the motion in this mode will eventually take this away, and the pendulum will come to rest. But you need the many body setting to see that. And that's why many body time crystals are non-trivial rather than these single few body or beam field examples.
Okay, so the next question is related to thermodynamics. Could you explain the intuition or what implies the no-go theorem for discrete quantum time crystals in thermal equilibrium?
Yeah, so the intuitive explanation of that is pretty much that, one is what I just said about first and second law of thermodynamics, and the second is just that, by virtue of coming to equilibrium, right, the very nature of coming to equilibrium means that you cannot detect the passage of time by making local measurements. Okay, so that's the extremely simple, intuitive answer, but then people actually define what you're looking for to define a time crystal in a very careful way, and then had various proofs about how you cannot get this in a Gibbs state. Okay, but the intuitive pictures are just things come to rest in thermal equilibrium, and according to the second law of thermodynamics, you cannot get a time crystal. I mean, it's the reason why you can't have perpetual motion machines, if you will.
Okay, here's an interesting one. Can time crystal phases exist whose period is not an integer multiple of the drive, but is instead intrinsic?
Yeah, exactly. So when I'm talking about crystals, time crystals, I have in mind systems that are periodic in time, but actually you can get time quasi-crystals, or you can get time glasses. So in all of these systems, you can have time translation symmetry breaking, but then you're not going to get any kind of period doubling in some exact sense. So a lot of many body localized systems actually can show you glassy dynamics, even if it's not exactly period doubled. And more generally, you can have period tripling and so on, but instead of having this kind of Z2izing like example, you can have Zn, and then you can get different kinds of multiplicities.
Okay. Would love to have time for one more. I have two more questions, but we can postpone it to the roundtable also.
Yeah, we also have time for questions during the roundtable discussion. So I think Anka already sent the link. The link is in the chat. Just click on it, and then you are in the meeting room for the roundtable discussion.